and playing around with numbers, when you come to zero, when you get zero, there's not a whole lot else you can do because 0 times anything is 0. So what we want to do is we want to figure out a way to continue our analysis and to deal with that 0. So what we do is we square everything. We take this number times itself. And everybody knows, even me, I know this, a negative times a negative is a positive. So I want to make all of these numbers positive. So make another column here and square each of these numbers. So negative 0.4 times negative 0.4 is 0.16, positive. Okay, so everybody got that? All right, now if we added all of those numbers up, this is what we get right here, this number. We get 19.36. And that is the sum of squared deviations. Excuse me, if we add all of these up, it's 34.4. And that's the sum of squared deviations, right? But that number looks a little bit out of place in our analysis because I'm thinking, I got 34.4 here. What does that have to do in relation to these individual numbers over here? It's pretty large. It's almost, yeah, it's twice as large as the largest score. That's 32, right? So the reason I have such a large number, obviously, is because I squared everything. I squared all of these and I added it all up. So what I have to do now is I have to do something else to figure out how to bring that number down. And the opposite of squaring things is to take the square root. Take the square root. So you divide the sum of squared deviations by n minus 1. So here's, there's 10 here, that's n, minus 1, because it's a sample, gives you 9. So 34.4 divided by 9 equals 3.82. That number is called the variance, But that's just the final step, or there's one final step in getting the square root. So what we do, or in getting the standard deviation, we take the square root of 3.82. So the square root of 3.82 equals 1.95. 1.95. So the standard deviation for these numbers is 1.95. So why is it important to know that number? So let me give you a little more information on that. So way back in the day, scientists and mathematicians were concerned about a lot of things. They always have been, right? Now everybody's concerned about COVID and things like that. Hundreds of years ago, scientists were trying to figure out laws of nature. Isaac Newton gravity, things like that. There were mathematicians that were observing nature. They were looking out at nature and they were saying, God created the world with order and nature tends to follow certain laws. And given sufficiently large numbers, a couple of mathematicians went about looking at nature. And so, for example, the mathematician, I believe it was Laplace, he was looking at a tree and he said, the tree, there's a tree outside my window right here. It's a eucalyptus. and it has a bunch of leaves on it. And if I took off every single leaf on that tree and I weighed them in grams, I would come up with, and I divided it by the number of leaves. Let's say there's 1,000 leaves on that tree. And I took every leaf off and I weighed each leaf, and then I added them up and divided by 1,000. I would come up with what? Which measure of central tendency would I get? For 50 bonus points.
Mean?
Exactly. You get the mean. So you get the mean. So what they figured out, observing nature, is that when you're measuring things in nature, nature tends to follow a normal or bell-shaped distribution. And there's certain properties in the bell-shaped distribution. One property is that within, if this is the mean, within one standard deviation of the mean plus 1 minus 1 standard deviation. That's the Greek symbol sigma, lowercase sigma, and that stands for standard deviation. And what they calculated is under a normal bell-shaped curve, plus or minus 1 standard deviation from the mean is approximately 68% of the curve. Okay? Do you remember that from undergrad or AP math? Under 2 standard deviations minus 2 standard deviations, this portion right here is about 95% of the curve, and 3 standard deviations is about 99% of the curve. Oops. Okay? So, given our scores of 13.4 with a mean of 13.4 and a standard deviation, 1 standard deviation equals 1.95, what that says is between plus or minus what is 13.4, 5, 3, 2, 15.35, and on the minus side, it's probably 11 something, right? Is it 11 something? 11, whatever it is. Between the two scores of, say it's 11.8 and 15.35, 68% of the class fell. 68%. So anybody that got a score between these two, between plus or minus 1 standard deviation from the mean, got a score that is pretty average, right? It's pretty average. And so if I told you, hey, I did great, I got a 14 on the nursing quiz, it's still within 1 standard deviation of the mean. But if I told you, hey, I got a 17, that's probably out there, I did better than 99% of the class. Does that make sense? So it's important to know what the standard deviation is, because it allows you to see where the most students fall, where most of the students fall. And it also shows you what the outliers are. Where are the outliers? If somebody performed plus 3 standard deviations from the mean, that's a really good thing. And the reason this is important is when we're conducting say we're conducting an experiment where we're giving people a pill, what we set the probability at is typically 0.05, right? We want to make sure that our effect, the effect that something is having on somebody, is in this range right here. This range right here. And with medicine, we typically set it at 0.01. We want to see a big effect out here, right? We want to see that change, that significant of a change. Does that make sense, or is that Too fast, too much? Let me give you a real life example, that doesn't look like this, but it'll help you understand this part right here, this range. So here's the example I always use. I know Professor Gaio is probably sick of hearing this. So when I was in school, when I was a boy, 70 years ago, I had to walk to school uphill both ways in the snow. You can't tell now because my skin is flawless, because I use L'Occitane from France. I had really, really bad skin. And I used to go to a dermatologist once a month. And my dermatologist, when I was in kind of junior high school, he said, you know, your skin is so bad that there is an experimental drug that we want you to try. And I mean, this is a long time ago. This is 40 years ago. So there's an experimental drug, and we think it's going to have an effect on people like you, and we think it's going to help your skin. So I'll give you the mad version of this. So say researchers, and I was part of this, say researchers took 100 boys, and we all had this bad skin problem. And there was a drug that was invented, and it was there was a clinical trial, and the clinical trial was being held at this junior college over in Westwood called UCLA. And there's no UCLA people laughing. Any UCLA people? No. Okay, so he said there's 100 of you, and they wanted to keep a really tight control on this. So we were all 16 years old. We were all white. We were all male. We all, kind of came from the same region of Southern California, and they took 100 of us, and they examined our skin, and we all had bad skin. They randomly assigned us to two groups. Oops. They randomly assigned us. There's an R. The top group had their skin measured again, and there's a way of classifying skin for this particular disease. And we all had to have type 4. So we all had bad skin. This group, they randomly assigned to this group, and they all had bad skin too. This random assignment was important. So how many people, if you took 100 boys and you put all of their names in a hat, and you shook up that hat and you drew names, the first 50 go into this group, the second 50 go into this group, right? They were randomly assigned. For this group, they actually got the treatment, right? The second group got a placebo, and they were both measured 4 months later after this drug regime. What is your hypothesis about the direction of the arrow? If the arrow is how your skin, what your skin looked like, what were the researchers hypothesizing the arrow would be like over here? Up, right, Shannon. Up. What is the hypothesis for this group down here? Down. No change, right? No change at all. If there were, this is sort of a future concept too, if there were 10 boys in this 100, and no matter what you did to them, their skin was not going to change, where did those 10 boys end up if we randomly assigned them to the two groups? Chances are 5 are up here and 5 are down here. And remember, no matter what you did to them, their skin is not going to change. If they all went up here, that would ruin our experiment. But because we randomly assigned them, we can just cancel each other. They can just cancel each other out. What if there were 20 boys in here, and no matter what you did to them, their skin would change? Where do those 20 boys go? If we randomly assigned them effectively 10 would be in this group and 10 would be in this group, and we'd cancel them out. Meaning I don't have to care about the particular characteristics of the participants if I have a large enough number and I randomly assign them to treatment and control. Okay? Everybody got that? So this is the hypothesis. At the end of the experiment, we don't want their skin to change by 1 standard deviation, right? This is just 1 standard deviation from the mean. If their skin changed by only 1 standard deviation from the mean, plus or minus, it didn't really change that much, right? So what they wanted to see was, did this group's skin change by more than 2 standard deviations from the mean? And actually, since it was a drug, they wanted to see if their skin changed more than 3 standard deviations from the mean. Like a big change. They wanted to make sure there was a big change. So my question is, anybody know what that drug was? Because my skin, I was in the treatment group and I haven't had a pimple in 46 years. Does anybody know what that drug was? For 50 bonus points? What is that?
Accutane.
Accutane. Right? So you're welcome, anybody that took it and has good skin. All right. So there we go. So that's why this is important, this issue. Okay, so, oops, where'd you go? Okay, so here's the normal curve. This kind of gets back to what we're talking about, right? There you go. That's what that looks like. Those standard deviations. The other thing that we can do when we have data like the one I just showed you is we can convert things into what are called z-scores. Z-scores. And z-scores are a way of it allows us to kind of compare apples and oranges. Apples and oranges. I'll give you an example of that in just a second. Here. Here's what a z-score can do for you. So, as you all know, I think you all know that most universities, I think, are doing away with the SAT for admissions and the ACT. But back in the old days, the SAT, the point of the SAT, one of the points was to be a check on your grade point average. So if you went to a school and you applied to a college and you say, hey, I got a 4.0, the thought was that you should score relatively high on the SAT. So the SAT was originally planned to be a check on your high school's GPA. And so this would be your GPA, right? So the year that I went to school, the year that I applied to college, I took the SAT, and in my day it was scored out of 1,600. And so the average score, the average SAT score was 1,000. Let's say with a standard deviation of, I think it's probably 150. So 1 standard deviation. So plus, this would be 1,150. And this would be 850. So within plus or minus 1 standard deviation from the mean right here, you had scores ranging from 68% of the people that took it scored between an 850 and an 1150. 2 standard deviations would be 1,300. That's doing pretty good, right? And then plus 3 standard deviations would be 1,450. And my friends that got over 1,400 on the SAT did pretty well, right? They're doing pretty well. One of the things, this is just a fun fact, I heard that all of the tech billionaires in Silicon Valley scored almost perfect math SATs, almost every single one of them, right? So in terms of GPA at my high school, Canyon High School, the average GPA would have been, let's say it's 2.0, with a standard deviation, say, of 0.5. So 2.5, 3.0, 3.5. And back in my day, we didn't have like honors classes where you get like a 5.0 GPA, right? So it's 1.5, 1.5. So if I applied to college and I told my college, hey, I have a 3.5 GPA, how many standard deviations from the mean is that? 3. It's 3 standard deviations from the mean. But if I told them, hey, I got 1,000, no, I got an 1150 on the SAT, how many standard deviations is that from the mean? 1. So they would go, there's something going on here. So what I just demonstrated was what's called a z-score. A z-distribution, and I wish I could do this, it's almost easier to do it with a piece of paper than it is on this whiteboard. A z-distribution is a hypothetical distribution. I don't know if you'll be able to see this. Probably can't see that. That's my z-distribution. A z-distribution, just think about it in your head. Think about it in your head like you have a transparency, where a z-distribution has a mean of 0. 1 standard deviation from the mean is 1. 2 standard deviations from the mean is 2. And 3 is 3. Conversely, -1, -2, -3. And when you have raw data like this, you can convert this raw data into a z-score. Okay? This is going to be a little tricky. You got to think abstractly for a second. So if I told you that I got an 1150 on the SAT, what is my z-score? What is it? 1, exactly. I have a z-score of 1. And if I told you my GPA was 3.5, what is my z-score? 3, exactly. So by converting things to a z-score, you can actually compare apples, to oranges. Because these things are measured differently, right? Your SAT literally is how many questions did you get right on a standardized exam. Your GPA is measured by the average grade you got in every class divided by every class, the number of classes you took. So these are not measured the same way. But by converting them to z-scores, right, we have a common way of measuring them now, and we can compare them. Does that make sense? Right? And so when we do this, we're able to take any number of things that have a metric that are measured, and we can actually compare them with other things that are measured differently. Is anybody in here, is anybody in here a member of Kaiser? I'm a Kaiser member, and Kaiser is really good at collecting data. They collect all kinds of data. And what they end up doing is I get a health report that's updated basically every single time I go into the doctor. And the health report, whenever I go in there, they take my weight. What's your weight? They take my height. They don't take my height all the time because they know it. They know what my cholesterol is, right? They know what my blood pressure is. They know what my waist, right? How do you spell waist? W-A-I-S-T. What my waist measurement is. 32. My waist is 32, but it feels so good when I buy a 38 size pants that I buy a 40. So they have all of these measurements. So weight and cholesterol are measured differently, but they can take my cholesterol and can compare it to all the other 55-year-old males in Kaiser Southern California. And there's an average for cholesterol for all of us. There's an average weight for people my height. There's an average blood pressure. There's an average waist. And they can take those and convert all of them to z-scores. And then they can actually build a model to predict my risk of having a heart attack in the next 10 years. Because they can take all of that data and smush it all together and compare it to itself, right? And build a model. And that's why the Z distribution or the Z-score is so important. Does that make sense? Okay. All right. So let me see where we are. All right. Does anybody have any questions yet at this point? Hit me. Hit me with questions. Nothing? Does any of it make sense? Okay. Let me look here. Okay, so the other thing I wanted you to see was there are some handouts that should be in kind of the packet that you have. Let me just show you really quick. This is an example. I won't go over all of this, but this may be helpful to you. I created this this PDF, and I like to use X's and O's. These are examples of research designs. And so sometimes you might be looking at research where you have an X and an O. You just have a treatment and an observation. This is the independent variable, that's the dependent variable. This isn't a very good research design because there's nothing to compare it to over here. There's no pretest. But sometimes we have to do this. It's called a one-shot case study. But if we have time, if we think ahead, we can add an O right here. And in this instance, we can compare this with this, right? But the problem with this design is that you don't have a group to compare it to down here. So in this design, you might have a problem because people may be involved in the study that just wanted to be involved in the study and they wanted to change. And that's called a participant effect, right? Or a selection effect. Because you're not really sure, why did people join your study? Excuse me. So you can add a group down here, but these are still not randomized groups. They're still not randomly assigned. Excuse me. I'm gonna have to go get a cough drop. All right, so this is the best design of all in science. This is called the randomized two-group pretest post-test design, where you have random assignment. This group gets the treatment, this group gets a placebo, and you're able to compare this to this, right? And this is called the gold standard or the old workhorse of science. This is the gold standard. This is called a Solomon 4 group. It's this design up here, but it adds 2 other groups, and you can see what's missing. This is missing this observation. And if you do this design, you can compare this group to this group, 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 etc. You can do multiple comparisons. This group typically takes a large number of participants. And then you have this where you don't have a pretest. And this is not as good as the one above, the randomized 2-group pretest post-test, but sometimes people do those. Then there are quasi-experimental designs where you don't have random assignment, but you're still trying to compare groups. This design right here is called an interrupted time series. This is also a longitudinal design. As a gerontologist, we like this design because you can observe changes over time with people. This is where you have a comparison group, but again, they're not randomly assigned. And then you have what are called correlational or ex post facto designs. These are the research designs that are going that way, that are looking at things that happened previously. Okay, so I just put that together just for your benefit. Okay, there are other handouts. One is on how to use SPSS, and then the last handout, it's in Word, is how to do. Let me see. how to enter information into SPSS. Okay, so from there, I would like to now do some examples in SPSS for you. But I'll stop. Does anybody have any questions at all about anything? Nothing? Does any of it make sense?
I
Yeah,
have one crazy question.
go ahead, Wendy.
Can you explain one more time how you got the Z-score of 1 with the SAT and the GPA?
Yeah, that's a good question.
Thank you.
Right. Super important. My wife has a master's degree in clinical psychology, and I was trying to tutor her and 2 of her friends over at our house. And so I got one of those huge Post-it things, and I got an easel, and I was drawing it out. I was drawing out the Z-score, and they were like looking at it like this. And all of a sudden, like the light bulb went on in their head. And I'm like, oh, something I said made sense. All right, so let me go back to the whiteboard.